Shuheng, and I'd like to thank all the organizers for putting together this wonderful meeting, and it's always a pleasure to be back in Santa Barbara, where I was a student back in the day. So I want to tell you about some new results on Fracton orders. I know this is a very broad audience, so I'll tell you what I mean by that and give some motivation. First, I want to acknowledge my collaborators, especially my very talented student, Evan Wickenden, who's really leading all of this work. And since we're here in Santa Barbara, I'll also mention my recent former student, Marvin Chi, now at Chicago, who was the UCSB undergrad. I also liked the sort of map from Nadi's talk, and if you know who all of these people are, then you can probably guess that this talk is located somewhere here. So we're all condensed matter physicists, except Agnes Beaudry is a mathematician, and that puts us somewhere in this overlap region. Okay, so before I tell you what Fracton matter is, let me tell you why we're interested in it. So there are many different reasons that one might be interested in Fracton matter, and things that have been of interest to different people in this room at different times. Something relevant to this meeting is that the whole subject is closely related to subsystem symmetries, but that actually will not be a perspective that I use in my talk. I think everything could be translated into that language, but I haven't found it most convenient to think in that language, at least for the moment. Instead, I'll take a maybe more traditional condensed matter physics perspective. I'll view Fracton matter as a class of quantum phases that are very much beyond our existing paradigms for thinking about quantum phases of matter. Okay, so let me give you a definition. So first of all, the setting for this talk is that we're interested in equilibrium, zero temperature translation invariant lattice systems with some finite range Hamiltonian. And what Fracton matter means is that there's at least one gapped excitation of restricted mobility above the ground state. Okay, and so to tell you what that means, let me remind you of this notion of superselection sectors, sometimes also called particle types or topological charges. So if you have a point-like excitation sitting somewhere in space, you can define an equivalence relation on the set of point-like excitations where you say that two excitations are equivalent if they're related by the action of some local operator. And the equivalence classes are superselection sectors. And then if you have a translation symmetry, you can hit an excitation with some translation, and you can ask, are the excitation and its translate in the same sector or not? And both possibilities can occur. If they are in the same superselection sector, then there's some local operator you can act with that mimics the effect of that translation, and the excitation is mobile along that direction, okay, given by the translation symmetry. So to define restricted mobility, if we're in d dimensions, our lattice translation symmetry is isomorphic to z to the d. We have some point-like excitation f, and you consider the subgroup of translations that don't change the excitation type of f. And it has to be isomorphic to z to the m, okay? And if m is equal to d, then that excitation is mobile in every direction of space, and we say it's fully mobile. Otherwise, m is less than d, and this excitation has restricted mobility. So Fracton matter just means there's at least one restricted mobility excitation. I'll give examples. So to zoom in a little bit more, in this talk, I'm also always going to assume three spatial dimensions, bosonic systems, so think about spin models, with an energy gap to all excitations, and for the most part, I'll assume that there are no loops, only point-like excitations. Okay. I also want to focus on abelian systems, which just means that if you take two superselection sectors and you fuse them together, you get a definite answer, and that makes the set of superselection sectors into an abelian group where the group operation is fusion. In Fracton systems, S is always infinite, okay, unlike systems of anyons in 2D, and usually it's not even finitely generated. Okay, so that is one of the things that makes this into a little bit of a complicated subject sometimes. Okay, I want to quickly run through kind of a key example. It's sort of the hydrogen atom of Fracton physics, the X-cube model due to Vijay Ha and Fu. And this is a Pauli stabilizer Hamiltonian, like Lukács mentioned in his talk, where you put qubits on the edges of a 3D simple cubic lattice, and the Hamiltonian is a sum of commuting terms. There are terms on cubes where you take a product of Pauli X on all the edges of the cube, and there are also vertex terms where you take products of certain patterns of Pauli Z's next to a vertex. Okay. This Hamiltonian is what we call a CSS Pauli code. It means that every term in the Hamiltonian is either a product of X or a product of Z. There are no terms that have both X's and Z's. And there are two kinds of excitations going along with the two terms in the Hamiltonian. You can make the cubed terms have eigenvalue -1 or the vertex terms. Okay, we get two classes of excitations. The interesting thing is that both these excitations have restricted mobility. So if you take a vertex excitation, there are different types. Take LZ, it can move freely in the Z direction, but if you try to move it, first down and then over, you wind up leaving behind something at the corner. So it can't turn a corner without leaving behind another excitation. Okay, so these vertex excitations are what we call line-ons. They can move freely along lines, along certain 1D lines, but their mobility is restricted otherwise. Okay. All right, what about the cube excitations? Here's a single one. If you act with a single Pauli operator, you can destroy it and recreate 3 of them. And you can move them around in patterns like this. What you see is that you can create and destroy these excitations at corners of certain rectangular membrane operators. And it turns out, if you think about this, that there's no way for an isolated fracton to move without creating other excitations. That means if you have an isolated fracton in energy-conserving dynamics, it will actually just be stuck forever if there are no other excitations close by. Okay. All right, so these fracton excitations kind of give their name to the whole field, but they also mean something more specific, these excitations that cannot move at all in isolation. Finally, one last kind of excitation. If you take composites of 2 cube excitations or 2 of these vertex excitations, you get what we call planons. They're mobile in certain planes of the lattice. Okay, so now I want to zoom out a little bit from this particular example and tell you about the status of work on fractons, maybe partly because during one of the breaks, someone asked me, haven't people moved on from this subject? I know the comment was well-intended, but I thought it was a good opportunity to make a joke. It is true, actually, that from the formal side of fracton physics, a good number of people did move on in the last 3 or 4 years. And the reason why is actually not because we learned so much and made a lot of progress, but because we know so little. And the questions are actually quite hard. There are lots of hard questions and maybe not a lot of ideas about how to make progress from where we are. So where are we? Well, there's kind of this very complex fracton landscape. So there are many, many examples of fractons in exactly solvable lattice models, but largely the bigger picture is lacking, despite the fact that there have been quite a number of interesting ideas that people who have come up with, including many people in this room. When I say that a bigger picture is lacking, I'm sort of thinking very specifically about one kind of picture you might be interested in this talk, which is a characterization of phases of matter in terms of their universal properties, in terms of properties that are the same everywhere in the phase. So we really know very little about that, okay? Surprisingly little, in fact. If you glance at the literature, you might think that we know more than we do. If you read the literature carefully, I think you'll realize that actually very, very little is known, okay? And so it's a hard problem to make progress in that direction. But we are actually now making some significant progress. So if you moved on from this subject, I think there are a lot of new opportunities that are opening up, and you might be interested to come back to it, or you might be interested to come to it if you've never been involved in it. Basically what I'm saying is that my collaborators and I have been having a lot of fun, and there's room for other people to join us. Maybe I shouldn't say that because it's also been nice to have this for ourselves, at least for a moment. Okay, so one thing that would be really nice to have that would really help with this goal of characterization is some kind of an algebraic theory of fracton orders. That's what this talk is about, and what I'm really thinking about is generalizing the algebraic theory of anyons, and specifically very simple algebraic theory of abelian anyons, since I'm interested in abelian systems. So let me remind you what that is. Okay, so the data that goes in to the algebraic theory of anyons is fusion and statistics. Okay, and here's a formal definition. So a theory of anyons, abelian anyons, is a pair of a finite abelian group and a quadratic form, which takes values. It's nice to have it take values in Q mod Z. Sometimes people might put a 2 pi in there, different conventions. So the elements of this group A are superselection sectors, anyon types, okay? And the group operation is fusion, and the quadratic form just tells you the topological spin. And from that, you can get the mutual statistics, which is a bilinear form. Okay, and a very important condition, which will play a very important role in this talk, is that this quadratic form theta should be non-degenerate, okay? And often this property is referred to as modularity or braiding non-degeneracy. And what this says is that given any non-trivial enyon, there's some other enyon that braids with it in a non-trivial way. And where this really comes from is something that has been stated more generally and called the principle of remote detectability, and it says that any non-trivial excitation can be detected by acting with some operator whose support lies very far away from the excitation. In this case, that operator would be a string operator of another enyon. Okay, and an important fact about this condition is that it's actually necessary and sufficient for physical realizability, and in particular, every modular theory of abelian anyons can be realized by some multi-component U1 Chern-Simons theory. So that's been known for quite a while. Okay, so this is what we would kind of like to have for fracton systems. So what can we say about that? Well, first of all, it's important to include a new ingredient in the data. In addition to fusion and statistics, we need some kind of information on mobility of excitations. Okay, and the only way that we really know how to do that is to assume, and it's a good way to do that, and I can make more comments on why this is a good way to do it, is to assume that we have translation symmetry, and that will formally make this set of superselection sectors S into a module over the group ring of the translation group. And we understand very well how this lets us encode both fusion and mobility properties into the module S. Okay, so that's kind of well understood at this point, work of a few years ago. All right, and schematically, the theory we want should be a pair of this module and some statistical data. Okay, but the problem is, one of the big problems is that we don't really know what this is. Okay, we know that it's interesting because we know that there are actually quite a few different kinds of examples of restricted mobility excitations that have some non-trivial generalizations of self and mutual statistics. In fact, even these completely immobile fractons can have a kind of self-exchange statistics, which is non-trivial in certain models. Okay, but what we don't know how to do is, even though we know particular examples of various statistical processes, we don't know how to specify the data for a full description of statistics in a given model or given this module S. Okay, so we don't really know how to specify theta. So this is sort of a very heuristic thing. Okay, there are many other issues too. Okay, that's not the only issue. One issue is that if you start to look at more examples of fracton models that I'll tell you, you'll realize that some of them are actually quite complicated, certainly geometrically complicated, and we probably need a simpler class of fracton orders to start with. And actually, I'll explain why this has not really been available in the literature so far. Okay, there have been multiple definitions of phase that appeared in the fracton literature, and it's not totally clear which one to use. And that's important if you want to talk about phase invariants, which are the same within phases to characterize systems. And we certainly need that because, unlike in abelian anyons, where we're typically interested in a small fusion group A, and where the algebraic theory A theta is itself a useful phase invariant because it's easy to compare between systems, really just because A is typically a small abelian group. For fractons, we know that our algebraic theory is going to be a large and complex object. Just because the module S is complicated, it's usually not finitely generated as an abelian group. Yeah, Nadi.
Case, there's a reason it's called modular. Because there's a modular.
Forget about the history of where modular. No. So no.
So the word modular is only by analogy.
I'm just borrowing the word modular from the way it's used in the theory of anyons. So and I know there's a history of it, coming from.
No, it's not history. There's a modular group,
right,
which has a well-meaning.
The modular group does not play a role here, as far as I know.
Okay.
At least not so far. Yeah. Okay. So right. So the point is that S is a large object, right? And what we really need are phase invariants that are easy to compare between different systems, and very few of these are known. Okay? And then there's another question which comes up, that even if we can identify this data, and in some very simple situations we actually can, it's not so obvious what conditions it should satisfy. Okay? So in the rest of this talk, I'll address these issues. So I'll tell you about a simpler class of fracton orders, and I'll tell you about phase invariants for it. I'm actually going to skip an answer to number 2, but if you really want to know, you can ask me during the question period. So I have an answer to that, which doesn't really play a very big role for the rest of the talk, which is why I want to skip it. And then finally, I want to tell you about the conditions that this data needs to satisfy in a case where we actually really know what the data is. Okay, so first I'm going to talk about these 2 points together. Yeah, Shuhen.
I have a question before you go into the algebraic theory. So for ordinary 2 plus 1D topological order, we know there's something that's not captured by the algebraic theory, right? Like the chiral central charge, the mod A part.
Absolutely.
Is there something like that that's not captured by the algebraic theory?
So the answer is definitely we don't know. So there may be things, right? It's not guaranteed at all that this algebraic theory is going to give a complete characterization of all the universal properties of a system. Yeah, so that's definitely something to think about in the future. So my point of view is just that it's a partial characterization, and so let's get as much information out of it as we can. Yeah, thanks for the question. Okay, so first I want to tell you a simpler class of fracton orders, but in case you're familiar with the literature, I want to tell you why some existing, maybe simpler classes of fracton orders don't quite do the job. Okay? I don't know if these are really previous attempts at coming up with a simpler class of fracton orders. That's perhaps a bit of a straw man framing. But something which was done pretty early on, which was to distinguish between type 1 and type 2 fracton orders. So all that means is that in type 1, there are some partially mobile excitations, some line-ons or plane-ons. And in type 2, all the non-trivial excitations are fractons. So the X-cubed model fits into type 1. I didn't tell you an example of a type 2 model, and I won't, but a famous one is Haas cubic code. Okay? And it's probably true that any kind of simpler fracton orders are a subset of type 1 fracton orders, but as a class, type 1 orders are not really simpler than type 2. And one reason, which is sort of a dumb reason, is that you can take a type 1 fracton order and a type 2 fracton order, and you can stack them, and you get another type 1 fracton order, which is still certainly as complicated as the type 2 order you started with. You could imagine defining that away, but there are also models from early on in the field due to Yoshida, which sort of behave like type 2 models in a plane, and then they have line-on excitations that are mobile perpendicular to the plane. And we certainly feel that those models are kind of as complicated as type 2. We don't have any good understanding of them. So type 1 is probably not going to help, but we probably want a subset of type 1. Another class, which I think is closer to what we want, is the foliated fracton orders, which, and I won't explain this in detail, but they're fixed points under a certain generalized renormalization group called the foliated renormalization group. And they do seem to be simpler, but there are a couple issues. One issue is just that it's not easy to check the property of being foliated. Given a solvable model, you need to find the RG circuit, and that can be hard to do even for people that have a lot of experience with those kind of calculations. Another issue is that it's hard to use this as a definition to start proving things and build a general theory. At least we don't know how to do that so far. Okay. Okay, so here is what we came up with, really stumbled upon in the course of trying to answer other questions. So we call an abelian fracton order P-modular, short for planon modular, if every non-trivial excitation can be detected by braiding with some planon. Okay, so here's some point like excitation X. It could be anything. It could be a fracton. You can braid a planon around it. And the assumption is that given X, there's some planon P where this statistical phase is not equal to 1. Okay, and that's not always true. Doesn't have to be true, but it is sometimes true. It's true for the X-cube model, for example. And it's usually not that hard to check this property when it's true. Okay. And one nice thing about this is that this property ensures that the principle of remote detectability is satisfied. It's built into the definition. And that's going to come back later. Yeah, go ahead.
Getting confused about the dimension here. So these are three-dimensional?
We're always in 3 dimensions now.
So it's like 3 plus 1. It's a three-dimensional model plus
Three-dimensional
time.
space, yeah.
And so what does so braiding a point around the point in 3 dimensions?
This is not topological, right? So this P is a planon. It's only allowed to move in this plane.
Right.
So its braiding with any point is well defined.
And so if you move the x1 lattice side up, then that
You might
vanishes?
not be able to move x1 lattice side up.
Okay, but it has to be in the same plane. And if
No, it could be offset by some amount. So there's certainly some locality. If you try to move x very far away in the transverse direction, eventually you're going to have to get 0. How you approach 0 could be complicated, but you have to get 0 eventually.
Thank you.
Can I ask another question?
Yeah.
So you said that this P-modular property is not always true, but maybe you could elaborate on what replaces the remote detectability criterion in general?
So remote detectability should always hold, but this is you don't have to be able to do it by planons. So for example, in Haas code, there are no planons, yet there is still a way, which is kind of complicated, but you can definitely do remote detection. It's a CSS code. There are X and Z sector excitations. You can make certain complicated surface operators. Really, you just take a product of all the stabilizers in some region. And so there's a way to do remote detection of, say, X sector excitations with Z sector excitations. We believe very strongly that remote detectability should always be true for sort of reasons that I'm not going to rehash, I think. But we don't know that it's always true. There's no proof. But we certainly know that this is not the only way to realize remote detectability, because the simplest example is just type 2 CSS Pauli codes that have no planons at all. They still satisfy some kind of remote detectability. Yeah, thanks. Good. Okay. So here's some examples. So these are there's not very many more, actually. I think these are most of the known distinct examples of P-modular fracton orders in Z2 CSS Pauli codes, like the X-cube model. Okay, so we don't need, let me mainly just tell you what the information is here, what kind of excitations you have. There's an important parameter called the planarity, which is the number of different orientations of planons you have. So if all your planons move in parallel planes, that's one orientation. If there are 2 different kinds of parallel planes, 2 orientations, and so on. Okay. You don't have to worry about the other columns too much. The FCC model is an interesting example that was actually constructed in the very first paper that Xie Chen and I, also together with Han Ma and Ethan Lake, ever wrote on fracton orders. It was really due to Han, kind of an amazingly brave and fairly complicated geometrical construction. And because it's a bit geometrically complicated, it has not been well understood. Okay, and one question you might ask is like, is this model somehow related to these other known models? Okay, and we answer that question in the course of this work. Okay, so starting from this definition of P-modularity, we can make some progress. We can start to build a bit of a general theory. schematically, one thing this lets us do is sort of package the fusion and some of the statistics information into a nice algebraic object that we call a P-theory. It's a pair of this module S and then bilinear forms that tell you the mutual statistics between each orientation of planon and arbitrary excitations. Okay, so there's one of these phi a's for every orientation. So this doesn't include all the statistical data, which we don't know how to include. And one thing this lets us do is define something that we call plane charges. So we say that two excitations are A equivalent if they cannot be distinguished by braiding with A-oriented planons. And we get some equivalence classes, and these form a module QA, which is the module of plane charges. It turns out that these plane charges have the same mobility properties as planons themselves. In the way translation acts on them. And you can think of QA as being generated by a stack of parallel planes. It's kind of a nice geometrical picture. And in a p-modular system, you actually get an injective map from S to Q. Q is something you make by direct summing up all the QAs. And this map is injective, so it labels excitations uniquely as a configuration of plane charges. So for example, in the X-cube model, the fractons wind up being charged under planes of 3 different orientations, linons in 2 different orientations. You can sort of visualize something about the mobility of these excitations right away. And an important quantity that this leads you to define is something that we call the weight, which is just the number of orientations of plane charges an excitation carries. Okay? And we also say that an excitation is intrinsic if you can't get it as a composite of excitations with lower weight. And both the X-cube fractons and linons are intrinsic. Okay. So now I'm going to go a little over because of the questions, maybe +5 or so. Okay. So from this, we can try to construct some phase invariance from this starting point. Let me just say that many of the known phase invariants are hard to compare, okay? Because they're not like this one, okay? This is a previously known one, where what you do is given a fracton model, you just wind up getting out a finite abelian group. And the way that you do this is you start with the module of superselection sectors, and you construct a submodule which is generated by all the planons, and you take the quotient, okay? But the problem with this is really that it's just one abelian group. It's enough to tell you some things about these models, but for example, it's not enough to tell you whether or not the FCC model is a stack of the other listed models, okay? So there's enough complexity here that you can just sort of think about this as there's not enough invariance in one abelian group to answer questions you might be interested in. So in p-modular fracton orders, you can generalize this. And the key idea is to take submodules generated by all excitations with weight less than or equal to I, and then you can form a whole sequence of quotients. You can argue these are phase invariants, and then you can compute this whole sequence for a variety of models. This is enough to prove that the FCC model is not a stack of the other listed models. And in fact, there's no linear dependence, except for the checkerboard model, which is known to be 2x cubes. There's no linear dependence of any of these models under stacking. Okay. Okay. So now I want to spend just a few minutes answering a different question. So what conditions should this data satisfy? And a way to motivate this question, given what we started with, is to ask, well, if we have this p-modular p-theory with the data that I described, do we know that it can be realized by some quantum system? And you might guess that the answer is yes, given what we know from abelian anyons, because remote detectability is satisfied, and non-degeneracy in theories of abelian anyons, that comes from remote detectability, and we know that that's sufficient for physical realizability, at least in that case. But there's an example that you can come up with, which is p-modular, but you can argue that it's not physical. And it's a very simple example. You imagine a layered system that has only planon excitations, okay? And in every layer, you have a Z2, so either there's a planon or not. Okay, and then you have to specify the mutual statistics. So we choose two excitations in the same layer to have vanishing mutual statistics. And if they're offset by a layer, we choose the statistics to be a half. This is normalized to 1, so you might also think about this as pi. Otherwise, the statistics is 0. Okay? And it's easy to check that this is p-modular. But the problem, you can see a problem when you take this and compactify it to 2D in the transverse direction, right? If you compactify the transverse direction, you get a 2D system. For a large enough compactification, that should certainly just be a theory of 2D abelian anyons. But if you turn on an excitation in every single layer, it's very easy to check that this is transparent to braiding with everything else. So you get a non-modular theory of abelian anyons, which is not going to be realizable. Alternatively, you don't have to compactify. You could also just consider infinite excitations, excitations of infinite support in the z direction, and the excitation where you turn on every single planon is also transparent. Okay, so what this really tells us is that there's a better question we should ask, which is what conditions, what extra conditions should we impose on this data to ensure physical realizability? And we can answer this question focusing on the planon-only case, where we only have planon excitations, like in this example. And you might think that this is sort of a boring case because it sounds, you know, a lot less complex. But we know that there are actually very interesting examples of planon-only fracton orders, which crucially are not just stacks of decoupled 2D layers. Okay. All right. So and we also know what the data is in this case. Okay, so we have a module S and some statistical data theta. In this case, we only care about translations normal to the layers. And so S is a module over the group ring of translations in the z direction, which you can also think of as a Laurent polynomial ring. Okay, theta is a quadratic form that tells you topological spin. And there's a spatial locality condition on it, which came up in one of the questions earlier, that if you take two excitations far apart in the transverse direction, you should get vanishing mutual statistics. We also make an assumption that all the elements of S are of finite order. This excludes some interesting but tricky examples, which actually have irrational statistics. And this lets us view S as a module over a Laurent polynomial ring with Zn coefficients. But these are kind of the obvious conditions, and our unphysical example satisfies all of them, so we're looking for something else. Okay, and the proposal is that remote detectability has to be upgraded. Okay, so here's an upgraded version. The first sentence here is really just introducing a new term, detector. We say that detectors are these operators far away from the excitation that are doing the job of detecting some excitation. Okay. Then there's an extra condition. So in addition to saying that every excitation can be detected by some detector, we want to assume that every detector actually detects something. Okay. There are no detectors that don't do anything, or the term that we introduce is every detector is effective. So this gives a pairing. It's a map from the set of detectors across the set of excitations, or superselection sectors, to R mod Z. And we expect in an abelian system these detectors are some string-like unitary operators at infinity. We don't have a general definition of them so far. For abelian anyons, we would identify detectors with anyons themselves because they're just string operators. And in this case, the reason that this effectiveness condition is not something you've heard of before, it's superfluous. Okay, that's why it doesn't come up. In our case, this is not, you could make a similar choice, but it's actually more natural to choose the set of detectors to be string operators for infinitely supported planons, which could live on the surface of a big cylinder like this one. Okay, and there's a way to define that formally. Okay, and improved remote detectability becomes non-degeneracy of a certain no longer symmetric bilinear form, and sort of the main result here is the proof of a theorem which says that improved remote detectability is equivalent to two other conditions. And one of the conditions is the fact that all of the compactifications are modular, okay, for large enough size, although you can actually remove that requirement. Number 3 is something that I won't explain. It's important for technical reasons. This is actually kind of the nicest way to think about these conditions mathematically, but these are probably the 2 more important conditions physically. All right. So, oh, right. And the important thing that I really should have said is that this condition number 2 is certainly necessary for physical realizability. So this theorem tells us that this improved remote detectability condition is also a necessary condition for a theory to be physically realizable. We do not know for sure that it's sufficient, okay? But at least in this case, we conjecture that it is, and it may be possible to establish that in future work. So there are some results that I didn't have time to talk about or make slides on, but what's coming next? Where is this going? I think there are a lot of things that are happening, but in the short term, what I think we will probably be able to do soon is come up with simple invariants for these planon-only fracton orders, where actually no simple invariants are really known already, at least not easily comparable ones. There is a way to generate a lot more examples of these p-modular fracton orders using gauging subsystem symmetries. If I really had my act together, I would have done that before this meeting, because it's more relevant to the meeting, perhaps, but it's not done yet. I also think that we will be able to get a better understanding of remote detectability beyond this simple planon-only case, and a better handle on what this algebraic theory actually looks like in more interesting cases where you really have some restricted mobility excitations like fractons and linons. Okay, stop there.
All right, thank you for the very nice talk. Any more questions?
Yeah, I was wondering if you could just elaborate on the definition of phases of fractons that you're using. You said you had kind of an answer to that.
I do, yeah, okay. I thought someone might ask, so I actually made a couple slides. I'm not going to tell the whole story, but so there's a problem that comes up in trying to define phases of matter for fracton systems. And the problem has to do with sort of interplay between your definition of phase and renormalization group. And what people observed is that, sort of one way to summarize it, is that if you use a standard definition of phase and you do one step of the RG, you actually wind up in a different phase. Okay, so you have RG operations that you have RG operations. So to make a system into an RG fixed point, you have to do kind of strange things to it in fracton systems. You have to integrate out systems that we would normally think of as non-trivial. And in doing that, you can change the phase that a system is in. But that's sort of very, you could say that that's kind of incompatibility between your definition of phase and the kind of RG you're using. And so you might like to change the definition of phase to fix that problem. And I think you do. And this actually led to a proliferation of different definitions of phase in the literature, which is confusing because now you had a situation where rather than just phases being equivalence classes of gapped systems, it was some kind of equivalence relation, but it also depends on what state you're starting with, which is a bit unappealing. And so the bottom line is that you can address these issues, and there actually is a single definition which is physically motivated, and it's compatible with RG. So these problems can be solved, and there are two key ideas that you need. The second idea is probably the more key idea. And this is just that you need to allow for certain continuous deformations of the lattice, if you're thinking about a lattice system. The sort of problem that you run into is if you start with a fracton model like the x-cube model, under standard definitions of phase, the x-cube model at lattice constant A is actually in a different phase from the x-cube model at lattice constant 2A. And so clearly doing this resolves that issue. And you can also physically motivate this because, of course, real lattice systems are idealizations of continuous systems, continuum systems. You can deform the lattice like this in the lab by applying pressure. So this is sort of the definition it's an extra equivalence. It's an extra kind of operation that you throw into your equivalence relation. You allow for certain continuous deformations of space.
Yeah, I was wondering, so the topological orders, if I only started with commuting projector models and then came to this general theory, I would find new topological orders that I couldn't have realized in the commuting projector models. I'm wondering, as you're developing your algebraic theory for fractons, if you're coming across fracton orders that you can't realize in commuting projector models.
Okay, that's a good question. So I think that there are fracton orders. There are some fracton orders that we already know of that I think certainly cannot be realized in commuting projector models. And so these are these examples that I very briefly referred to that have irrational statistics. So these are, the way that we realize them is using infinite component Chern-Simons theories. So these are 2 plus 1D Chern-Simons theories with an infinite K matrix which has some band diagonal structure. So the coupling between, you can think of each Chern-Simons gauge field as related to some layer in the Z direction. And then there's some coupling between layers built into the K matrix. So in theories like that, you can get irrational statistics which decays exponentially with increasing spatial separation. That's something you definitely cannot do in a commuting projector model. There are probably those examples only have planons in them, but there's no reason to believe that that kind of phenomenon is limited to planon-only theories, and there probably are other examples like that that have not been discovered yet.
So is the intuition for this P-modularity definition that we are still kind of secretly building the fracton order using some underlying 2 plus 1D topological order? Because the input is something like an ordinary braiding between anions on a 2D plane. Is that the right intuition?
Maybe to some extent. I mean, it's certainly true that, let me tell you a fact that goes contrary to that intuition. So there are examples of P-modular fracton orders where all of the mutual statistics between planons and any excitation, and also statistics between, so if you just look at the planon statistics, either statistics between planons and planons or mutual statistics between planons and other excitations, there are examples of P-modular fracton orders which are distinct. They're in different phases, but that's not enough information to tell them apart. And so the example that's well understood is the X-cube model and what's called the semionic X-cube model. And the way to distinguish them is to look at a kind of self-statistics between line-on excitations. And it's rather complicated because it's like you have two line-ons moving along the same line and you want to exchange them. So one has to move out of the way by splitting into a bunch of other excitations, and then you can bring it back and they go past. So you can define a notion of self-exchange statistics, and it turns out that that's what you need. You can prove that those two models, they cannot be in the same phase. There it depends on how you define phase. But under this deformable lattice phase definition, definition of phases, they are in different phases. Nonetheless, I mean, there's definitely also an element of truth in what you're saying. I think there is some intuition that like a lot of what you're specifying is the information of some 2 plus 1D building blocks. But maybe it's a little bit beyond that somehow.
So I have some question about the entanglement RG. So do we always expect the fractal orders will bifurcate or even like multifurcate under the ER? Or like, can we use this bifurcation as maybe a definition of fractal order or something?
Yeah, that's a good question. I mean, so I don't know. So the short answer is I don't know. I actually don't even have a proof that like an abelian fracton order has to be, like an abelian fracton, it could be that there exists an abelian fracton order that's not a fixed point under entanglement RG at all. We don't know an example of that, but I don't know a way to prove that that doesn't happen. So that's one point. Another point is, I think it's tricky to use that as a definition because examples that can't be realized in commuting projector Hamiltonians won't really be fixed points of entanglement RG. And so I don't know. Unless we also change what we mean by entanglement RG, then it seems a little bit challenging to use that as a definition.
All right, in view of time, we should probably move to the next talk. Let's thank Mike again for the very nice talk.